Today we're going to be looking at another one of Veritasium's videos. Specifically, what if you just keep zooming in? Well, those people that think the universe is a simulation would probably just say you reached the point where it's all pixelated because the devs stopped caring. Those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see.
This is a tiny piece of metal just 3 millimeters across. And here's what happens if you just keep zooming in. 1,000 times,
Cool.
100,000 times, 50 million times. Each of these blobs is an actual atom. I saw this the other day at the University of Sydney, and it kind of blew my mind, because up until just 30 years ago...
Now, you can't do this with a basic light microscope, because visible light is electromagnetic radiation between 400 and 700 nanometers. And here you're dealing with stuff that's less than 1 nanometer. So, yeah, he's using an electron microscope or something similar.
Directly seeing atoms like this was thought to be impossible.
The rooms that you're going to see here are perhaps the most shielded rooms on campus, or even in the whole of Sydney, I would say, and perhaps also the most expensive.
That's wild.
I'm not sure what he means by most shielded. I'm pretty sure Sydney does have a research reactor, though those don't require nearly as much shielding as a commercial nuclear power plant just because they're a lot smaller. But sure, these kind of microscopes are well protected.
That's wild.
So why is it so hard to see atoms?
Well, you can't actually see atoms with visible light.
Yeah.
That's because while light has wavelengths between 380 and 750 nanometers, an atom is still over 3,000 times smaller, just 0.1 nanometers.
Yes.
And if the wavelength of light is much bigger than the thing you're trying to see, the light will just diffract or bend.
Which is why you gotta use particles with much smaller than atomic wavelengths, such as electrons.
Around it, so you won't be able to see it.
So if you want to see atoms, you need something with a much, much smaller wavelength. The best candidate isn't even light. It's electrons. In
Yeah, light with a wavelength of 0.1 nanometers is going to be an X-ray.
1924, a French physicist named Louis de Broglie worked out that everything was sort of wave-like. Not just light, but matter too. Atoms, molecules, even you yourself have a wavelength.
And
Yes.
the formula for this wavelength is Planck's constant divided by the object's momentum, that is, mass times velocity.
Now this comes up in nuclear engineering a fair bit. This de Broglie wavelength, this determines how neutrons interact with matter in a nuclear power plant, whether it be something they're about to fission, whether it be a control rod, if they get scattered, if they get absorbed, due to these wave properties. Now when he said even you have a wavelength, compared to atoms, we're really big. The thing is, our waves are really, really small because Planck's constant is a really small number. 6.6 and some change times 10 to the minus 34th. So you're dividing by your mass in kilograms times your velocity, how fast you're going. So you're going to get something on the order of 10 to the minus 35, 10 to the minus 36 meters as your wavelength, or about 25, 26 orders of magnitude less than that of an atom.
So here what you actually see, that's the column of the microscope where we accelerate the 300 keV electrons down.
300 kilovolts, these electrons.
Yes. So they are relativistic particles.
How?
300 keV is a fair bit for an electron. And yeah, that's going to be 70-something% the speed of light. Now, an electron volt is a unit of energy. Simply the charge of an electron times a volt, you get energy. Now, it's very small on a macro scale. It's 1.6 times 10 to the minus 19th joules. And a joule's pretty small on a macro scale. A 1-watt LED operating for 1 second uses a joule. But for an electron, 300,000 electron volts is a lot.
How fast are they moving? 99% the speed of light, or?
Well, around 80.
80% the
Okay,
speed
that
of
was
light.
close.
Yeah. So what would be their wavelength?
The wavelength is the Planck constant over the momentum, right? So if we calculate that, we come to around between 2 to 3 picometers.
Whoa!
Yeah.
That's over 100,000 times smaller than visible light, so theoretically, you get 100,000 times more resolution.
A picometer is 10 to the minus 12 meters. A lot of interesting units showing up in this video. I love it.
Shortly after de Broglie's discovery, a group of scientists in Germany started working on a microscope that would use these high-speed electrons.
The only problem is you can't bend electrons using glass lenses. So how do you focus them?
Well, they have charge, so they can use magnetic fields.
Hans Busch, a German physicist, suggested that an electromagnetic lens might do the
There you
trick. He published his results in 1926, but never actually built one. Fortunately, a copy of his paper fell into the hands of an eager young PhD student, Ernst Ruska.
Okay, he's the
Ruska
one
built
I've
his
heard
first
of.
prototype by
I haven't heard of Hans.
oiling up some wire and surrounding it with iron, taking care to leave a gap in the middle. Then, when he passed a current through the coil, it induced a donut-shaped magnetic field through the metal and across this gap. This was his lens.
It kind of looks like what's funny is it kind of looks like a tokamak-shaped fusion reactor or a circular particle accelerator. Basically thing that uses magnets to move something in a donut shape. It's interesting how often that comes up. But here we're dealing on a much smaller scale in terms of energy.
To test it, Ruska first boiled electrons off a tungsten filament, the same
Boiled
kind of filament you'd
electrons.
find in an incandescent light bulb. He accelerated these free electrons through a positively charged anode down to his electromagnetic lens. As an electron approaches the lens, the magnetic field exerts a force on it. So if an electron is traveling in the y direction and the magnetic fields are in the x direction, this force, called the Lorentz force, pushes it in the z direction. But as the electron moves this way, it encounters other magnetic field lines along the donut shape, which constantly point its
guides
motion
it.
in a circle. But then this circular motion means the Lorentz force starts pushing the electron inwards as well, spiraling it into the center of the lens. Now,
Now
if
it
you
goes
trace
down.
the path of the whole beam of electrons, you'll see they all get steered into the center, focusing the beam.
A little thing. I have to say, Veritasium's getting really good at its quick explanations of things that were more or less entire lectures in a matter of seconds.
By 1931, Ruska and his colleague Max Knoll used this kind of design to build the first working electron microscope. It was pretty basic, made of brass roughly bolted together.
Looks really old school.
But
Yep.
it worked. The image itself was created once the focused electron beam hit a sample sitting at the focal point. The sample needed to be
that.
incredibly thin, only around 100 nanometers thick. More electrons would make it through the thinner parts of the sample than the thicker parts, creating an electron imprint of the sample. Then a second electromagnetic lens magnified this imprint down onto a fluorescent detector, producing the final image. This was known as a transmission electron microscope, or TEM.
You could use something like this to analyze radiation damage in nuclear fuel and materials in the neutron field that gradually get neutron embrittlement over the course of life. The limitation on using something like this is it's small and it has limits on thickness in addition to sample size, so it would take a really long time, but you theoretically could. But this was made in the 1930s, so people barely knew what a neutron was at this time.
Now, early versions of the microscope barely magnified at all. In fact, it wasn't even better than an optical microscope. But Ruska was determined. Over the next few years, he experimented with adding more lenses onto the microscope to create bigger and bigger images. By the mid-1930s, Ruska had gotten the TEM way past 10,000 times magnification. It could produce close-ups of insects, bacteria, and even viruses at a level far surpassing the optical microscope.
That's true, yeah, I was going to say, certain small viruses you wouldn't be able to see on an optical microscope, so that's cool.
But right as Ruska's TEM was taking off, a German physicist named Otto Scherzer published a paper claiming that the microscope was about to hit a brick wall. There was a flaw in the electromagnetic lens, he wrote, that was completely unavoidable. For an electron to make it to the focus of the lens, it needs to be deflected by a specific amount. If you simplify its trajectory, you can define that ideal deflection with this angle theta. This angle depends on the horizontal distance of the electron from the optical axis, and how far down the axis the focus is, also known as the focal length. The shorter the focal length, the stronger the magnification. If you graph this angle as a function of distance to the optical axis, you'll see that it can be approximated as linear. The problem is
the
that the
metal.
magnetic field doesn't scale linearly.
No.
It's much stronger near the edges of the magnet.
Yes.
So if you plot the curve for the actual deflection of the electrons, you'll see that the magnetic field over-deflects the electrons further out. Their angles are bigger than they should be, so they end up focusing before the rays in the middle. And as a result, the focus is spread across the optical axis instead of being contained in a single point. The blur starts out around the edges of the image, but it gets worse the higher the magnification. This is called spherical aberration, and it distorts every radially symmetric magnetic lens.
In fact, it doesn't just affect magnetic lenses.
Every spherical lens, from a camera to a telescope to a magnifying glass, also suffers from it.
But there is a surprising
Yes, technically, you'd even see it in stuff like mirrors, especially those more globe-shaped mirrors that are designed to see around corners and like office buildings and stuff.
simple way to minimize spherical aberration. Just add a second lens, one that diverges light instead of converging it.
Now, a diverging lens also suffers from spherical aberration, but if it has the same amount of aberration as your converging lens, just in reverse, you can stack the two to essentially cancel out their effects, and that removes the aberrations almost entirely. Almost all modern lens systems in cameras and microscopes use some sort of correcting divergent lens.
So you might imagine that the TEM simply needs its own version of a diverging spherical lens to magnify further. But with magnets, this is physically impossible.
Every magnet has two poles,
yeah.
a north and a south. It's impossible to just have one. Even if you split a magnet down the middle, it creates two smaller magnets, both with a north and a south. And all magnetic field lines have to start at one pole and end at the other, forming...
Yeah, if you somehow tried to create a magnetic monopole, it would destroy itself. Though I'm not sure if it would be constantly emitting energy or constantly receiving energy. Either way, it's going to go away. It'll just emit itself away, or it'll absorb so much and then it'll explode.
A closed loop.
Is a direct result of the second Maxwell equation, because the field that you create has field lines that start and end at the same magnet. So the electrons will always cross through two lines. The first time it passes through by the Lorentz force, it's brought into the spiraling motion, and then the second time, from that spiraling motion, which has then a slightly different direction, it's pushed towards the axis. That's why all electromagnetic lenses, by default, will converge the beam and never diverge it.
Even if you shot electrons in from the other side of the lens, they would still get focused.
Yeah.
This is what Otto Scherzer's paper proved in 1936, stopping progress on the TEM. It is impossible to produce a radially symmetric magnetic lens that diverges.
And this was, of course, a big roadblock for the development of electron microscopy, because people saw, okay, we can accelerate electrons as much as we want. The presence of the spherical aberration will always be in the way.
Because of this roadblock, advancements in the microscope's resolution slowed significantly. By 1955, another microscope beat the TEM to the punch and took the first generally accepted image of atoms. This was called the field ion microscope, and it worked by shooting helium or neon atoms at an atomically sharp...
So here you're using ionized gas, which also produces a smaller wavelength than visible light.
needle tip. The tip was positively charged, so when the gas atoms hit the needle, they got ionized and were ejected off perpendicular to the surface. And that could form an impression of the atomic structure of the tip. But this method was limited. You could only get a sense of the atomic structure of the very tip of the needle. And the images weren't all that...
So just the tip. Also, sample preparation would have to be extremely precise. Nanometer precision.
Impressive. Luckily, Ruska's electron microscope wouldn't stay stuck in the realm of insects and bacteria forever. Despite Scherzer's aberration limit, work on the transmission electron microscope continued. During the next 4 decades, people tried boosting the resolution with clever workarounds, and perhaps none more so than British-American physicist Albert Crew. His idea was to replace the tungsten filament, which fired off electrons at random, with a more directed source. So instead of boiling electrons off the surface, he tried pulling them off with a stronger electric field. And by sharpening the tungsten into a fine tip, he was able to create a narrow beam which was over 1,000 times brighter than before.
He paired his new narrow beam with an unlikely technology.
The cathode ray tube TV.
Yes, that's
These
what
TVs
this
worked
nice.
by scanning an electron beam across a screen. The screen was coated in a phosphor that produced light when hit by electrons. And by varying the intensity of the electron beam, you could vary the brightness of the screen, giving you a black and white image. Crew was inspired to design a similar electron beam for the TEM that would scan across the nanoscopic sample. So instead of creating an imprint of the whole sample at once, Crew's electron beam made smaller imprints, mapping the sample out bit by bit. This wasn't the first time someone had tried to make a scanning version of the TEM. German researcher Manfred von Arden built an early prototype in the 1930s. But it was destroyed during World War II.
Mentioned 1930s.
When
I
Crew
figured.
revived Arden's design, he made several drastic improvements, and by 1970, he had this, the first image of single atoms taken with the electron
Oh,
microscope.
that's cool. Especially for back then. Wow.
Researchers quickly jumped to employ his tech, producing countless images of atoms. After nearly a century of improvements from Ruska, Crew, and many others, the magnification upgrades on the TEM had reached their peak. But Scherzer's problem persisted. Spherical aberrations set a hard limit on how small you could see. Even Crew himself gave up on trying to get around it after over 10 years of work.
One thing about this, the scanning TEM, is it would also involve a higher radiation dose compared to the TEM, because you're simply more electrons. So you probably couldn't use something like this on a fragile material, but that's a trade-off that you need to make while using this additional. So it's not completely non-destructive, depending on what you're using this on.
Unfortunately, we could never make it work. After many heartbreaking attempts, we were forced to admit defeat. Around this time, other microscopes emerged that could also image atoms. These probe microscopes work by gliding an
Scanning
incredibly small
tunneling.
stylus across the sample. The stylus detects variations in quantum effects or nanoscale forces.
So the scanning tunneling measures quantum tunneling current, which is pretty cool, so you can actually map the atomic structure. Though, that one only works on materials that are conductive, so any ceramics, including ones that are used in nuclear reactors, it's just not going to be any good. Not to mention, it's going to be extremely sensitive to vibrations, which just kind of goes with the nature if you're that sensitive to something like quantum tunneling. So you need to put it in some sort of isolation containment structure, if you will.
To then map the surface structure of the sample. These were easier
That's
to build, and
interesting.
because they didn't use any lenses, they weren't limited by spherical aberration.
Yeah, the atomic force, you're using the forces generated by the atoms themselves, rather than signals from the electrons. Though there, the invasive part is using a probe versus using electron bombardment, but also take longer to do.
Their images were even 3D.
A lot of trade-offs in this.
But the looming issue was that these probes weren't really seeing atoms. It was more like feeling atoms.
Throughout the 80s and 90s, this was all we had.
I see what you're
But
saying.
what if there was another way? Scherzer's theorem proved that a diverging radially symmetric lens isn't possible.
But if you're willing to give up on that symmetry, well, the theorem no longer applies. The problem is that radial symmetry is arguably the most important property of any lens, because if you break the symmetry, you also break the image.
But three maverick scientists thought there might be a way.
Scientists.
Knut Urban, Max Hayter, and Harold Rose were known in the electron microscope community as troublemakers. And for years, barely anyone had been interested in their research. Or more importantly, in funding it.
Yeah.
And for a good reason, too. Their idea was kind of crazy. I mean, they purposefully wanted to break the image using a lens that wasn't symmetric. Their hope was that there would be a small part of this distorted image that would be slightly diverging. And maybe, just maybe, this small part could correct the spherical aberration of the original lens. So they got to work.
To distort the image, they used a massive nest, 6, 8, or even 10 separate coils and magnets with bumpy
cool.
magnetic fields.
Bumpy
These were known
and
as the
hexagonal.
hexapole, octapole, and decapole magnets. So as the electron
Exactly
beam
what it
passed
sounds
through
like.
a hexapole, it would twist and squeeze the flat 2D image into a triangular saddle. And the circumference of the original beam would be pushed into the three corners, with the rest of the interior stretched out. But now, the middle of the image would have a slight concave bow, giving the effect of a small divergence. Then, Rose, Hayter, and Urban forced the beam through a second hexapole, one that worked the opposite way, so it would unbend
Basically
the distorted
bend it
image
back out.
back into a circular shape. But now they calculated this new image might have the remnants of that tiny divergence still in its center, with spherical aberration pointing in the opposite way. So if they got their maths and engineering exactly right, they could feed an image with spherical aberration through these two lenses to almost completely counteract
Now
the
that's
effect.
cool.
And I imagine a lot of people in the field thought it was a crazy idea when it was proposed, right?
Not only the concept, but that this is like technical feasible, I believe. It was thought that this is not possible.
By May 1997, the group had just 2 months of development time left before their last sponsor withdrew their backing. And to make matters worse, their latest lens iteration was still just on the drawing board. But somehow, by the 23rd of July, just a week before their funding ran out, the new lens was ready to test. They gingerly placed it into the microscope, but like every time before it, the lens was unstable and failed. So they decided to switch off the equipment for 24 hours to allow the magnets to settle. And then at 2 a.m. on the 24th,
always
they
at 2
turned it on
a.m.
again. And almost magically, the picture started to stabilize. Suddenly, there was no aberration, only beautiful, clear images of atoms. After more than 60 years of failed attempts, Urban, Rose, and Hayter pulled off the seemingly impossible. With this method, they cut the resolution of the TEM down to only 0.13 nanometers.
Wow.
An average TEM image went from looking like this
I'm going to say a hydrogen atom's about 0.1, so they're getting pretty close to smallest atoms.
to this. A few months after the group's breakthrough, Newt Urban attended a microscopy conference to share these results. But because of the group's reputation, he was relegated to a small back room that barely anyone noticed. Soon, however, word spread that against all odds, his pictures seemed real. Then a crowd of hundreds formed. People were lining up outside, hoping to get a glimpse of their stunningly sharp images.
So we're gonna get a sample holder.
Yes, now we get a sample holder out. We put that under the optical microscope. So the sample itself is a small lamella that you can't see without the optical microscope. Yeah, have a look through that.
Nice.
Beautiful. On top of the B, there's a prong.
Yeah. And on the very top of that, on the left-hand side, looks like a little bit of dust. That's our actual sample.
Yeah, sure. That's awesome.
Okay, now I simply go up with the magnification.
I just love it. The sample holder you need to see on a regular light microscope, but then the actual sample we're going to go ahead and put into the electron microscope. That's amazing.
And I do a very few, like more basic alignments. In this electron microscope, because it's called transmission electron microscope, the electrons always transmit the sample. Here we look through our entire sample at the same time. And that's why it's so important that we align the sample. If you imagine atoms in a high symmetry direction are lined up like pearls on a string, when we look down it, well, we can see an image. But if we're in like some random direction, then everything will be just blurred. So that's why we have to do some tilting in the end. And this is where the actual sample starts, the strontium titanate. And this is the thin region where we
strontium,
hope
nice.
to get atomic resolution.
So this is 5,000 times?
Yes.
Wow.
And we see strontium, titanium, we see oxygen, we see carbon. That's
Oh, you're looking at the full spectrum. Yeah, this reminds me of when I was in college and you would have an unknown sample and say, I don't know, look at it and see what it is. Of course, you wouldn't be using a microscope. You would be using, a system of radiation detectors and it would be radioactive, but this is still sort of the same thing. It's the same general concept of, seeing what what everything is, what all their characteristic peaks are.
Contamination, so most likely what we're looking at here is carbon contamination.
When you do this focus, what are you really looking for?
I look for this edge to become sharp. See atoms.
What?
Just like that.
Just like that. That's wild.
That's cool.
Shortly after the group successfully corrected the aberrations in the TEM, Andrei Krivanik independently achieved the same for Kru's version of the microscope, the scanning TEM. And in 2020, all four were awarded the prestigious Kavli Prize in Nanoscience for accomplishing what so many others thought impossible.
Awesome.
Through their persistence and ingenuity, seeing atoms like this is, well, normal.
How big of a difference does aberration correction make?
If you want to see atoms, and if you want to, for example, measure interatomic distances, and if you want to learn what type of atoms you have, you need aberration correction. Any research that's materials science, materials engineering, chemical engineering, you need to
Gonna add nuclear engineering to that too.
see what's happening at the atomic level, because you want to relate the properties to the structure.
Of course, the next step would be to look at subatomic particles, but we're just not there yet. The only way we really observe them, and probably the closest you can get other than to looking at them, would be using particle accelerators. Because even, observing fission events at a nuclear power plant, it's all detectors, counters, the observance of heat, but not actually directly seeing all these little diagrams you see of like a neutron pinball splitting a big nucleus. I mean, those are all just artist representations of what's actually occurring. That's not actually what it looks like. I think the closest as far as observing would be on electron microscopes, how they showed, you can kind of see the cloud, so to speak, of the electrons, but not a free electron by itself, just like areas where the electron has a higher probability of being located.
Can't see the structure at the atomic level, you only have half of the information. So that was a game changer. That's why nowadays every university in principle needs a microscope like that.
Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.